So continue from the past video, we have S equal to 165 millimeters. In that 165 millimeters, we have verify some assumptions here that is shown here. Now we just need to do some detailing as from the questions. We now work and we find the spacing close to the support A, and that is in this region. So we can just draw this this view here, that I draw it here. Now there is a quick notation here. The first fitments that should start at 50 millimeters. Now that is given in the standard in clause 8.3.2.3. now on the page number 125, on the page number 125 on clause 8.3.2.3, we have a line here, the fitments. So the first fitment, so this is the first fitments at each end of the span should be positioned not more than 50 millimeters. So we cannot put the space more than 50 millimeters. So the first fitment should be placed up to 50 millimeters. You can put less than 50 millimeters, but not more than 50 millimeters. So that's the logic here, that we put the first fitments at the close. This is support A, so this is support A. Now this support A, close to the support A, 50 millimeters we have, that is the first fitments. Now we need to find this distance. As I mentioned, we know this distance from the previous calculations. We know this which is this one, 1013 millimeters. Now we can't take 1013 millimeters, as you know, we have to extend up to distance D. So I have 1013 and then I plus D, and that D is the nothing but given in the questions, that is 650 millimeter, which is the depth of the beam, that is plus, so that is given 166.3 millimeters. Now this is measured from the center of the support. So if I want to find this space, which is 1663 minus 150 is nothing but, because you can see the support has a 300 millimeter this distance, so it's measuring from the center, so it is 150 minus this first 15 is 50, so that is give us 1463 millimeters. So this distance from this first fitment to the last fitment is a 1463 millimeters. So now we need to know how many fitments we can put here. Now to find a number of fitments, we can have 1463 divided by this distance is 165 millimeters. That spacing that we found here, that in this zone we have a spacing of 165 millimeters. That spacing we use it here. So we can say 8.8 is, we can't put 8.8 fitments, so we rounding off 9 fitments. So we can provide the 9 fitments as the spacing of 165 millimeters. And from this line, which is actually showing it here, that from here to here, and from this line onwards, which is this line from here, we can provide this 326 millimeter, more than 326 millimeters. So that's the spacing in this zone. Now we like to find at the support B on the A side. So what we found so far we found the I can summarize this one. We found here, which is 165 millimeter spacing. We also find 326 millimeter spacing. Now at support B, we need to find how much spacing we can provide. Even this one is more critical. You can see they have a larger shear force here. So definitely we will have a spacing which is smaller than 165, because we need to resist this high shear force. So now we are working close to the support B, and we need to find what is the spacing in this region. Now at support B, so we need to find at support B how much spacing we are providing it, and it's on the A side. So I'm talking about on the A side, how much spacing we're going to provide on this side, not this side but on this side. Now we are working on. Now cracking cannot extend into the support. So for example, cracking will not happen in the supports, but the cracking will going to start from some distance from the support B. So the calculate VBA at a distance of D0 from the face of the support. So that is, we need to find the cracking will start generally D0 distance. Now this is given in the standard. Now that is written in the standard in the clause 8.2.3.2 on page number 115. It is clearly written that the maximum transverse shear near a support is at a distance of d0 from the face of the support. So therefore we can't start this. So it means that the cracking generally start at a distance d0 from the support B. So for that case we can draw these figures here, and we have these supports, which is support B, this is support B, support C, and this is support A, and we need to find the distance d0 from the support A, and this is 150. So basically we are interested in this shear force. What is this shear force? That is our design shear force. We can't take 437 because the cracking is not at the 437. The cracking generally starts far from the from the support, because we have concentric reaction force. That concentric reaction force has an effect, so the cracking does not start here. There may be some different scenario, but not for the shear cracking. Now in this case we are calculating this one. Straight line equations. V star is a shear force. The slope is minus 150, is a downward slope, so minus 150x, and the intercept 437, and we need to find this distance x. So let's say this is the distance. Let's say from here to here, this distance is x. X is nothing but basically d0. Now we calculated d0 in the first steps. We calculated d0 value. D0 equal to 526 millimeter, which is 0.586 meters. Now in that case we substitute 0.586 meters plus 0.3 divided by 2, which is 0.150. that is just measuring from this half of the support, plus 437, it gives us 327 kilonewtons. Now again we have these equations. I think in the previous video I explained that equations in the page number 115. On page number 115 we have these equations. Vu is the capacity of concrete plus capacity of steel. We are taking 0 because of no pre-stress. So V star is equal to 5 Vu, and Vu is nothing but Vuc plus Vus. So that's I written here. We substitute VBA star equal to capacity reduction factor 0.7, and we have a VUS 157 that we calculated in the previous steps. VUC we calculated 157. Please note VUC is constant. It does not depend on the spacing where the supports are. So we are not calculating VUC regardless of where we are calculating. The VUC, the capacity of the concrete is constant. So we are, regardless where we are providing the reinforcement here, the fitments here, anywhere in the beam, the VUC is constant. So we always have VUC constant 157, and this one vary because this one depend on the spacing, how much fitments we are providing and spacing. So VUC always vary depending on the number of fitments. So if you simplify that one, we will get VUC equal to 310 kilonewton. Now we have an equation for the VUS. We have an equation for VUS. That equation is given in the clause. This is the equation for VUS, this big equations, and from that equations we can calculate this S. Now I written it here. I bring this S across VUS here. I substitute the value. ASV 160 that we found here. Area of the fitment 160 millimeter square. FSY is 250 megapascals that we calculated, that we assume here. Before dV is 527. dV we predicted dV 527 millimeters. VUS that we just found it. VUS we found 310 kilonewtons. And please note we need in the newtons, so we just multiply by thousands. And cot 36 is given in the standard. 36 on the clause 8.2.4.3 we have a theta v value is given here in the standard, which is 36 degree, which is nothing but the angle of the crack. So if you simplify that one, it gives us 94. I'm just taking the rounding number 90 millimeters. Now clause 8.3.3 states that the fitment spacing will be provided for a distance d from the cross section in the direction of decreasing shear. So what does it mean? That now we have a same scenario in the previous calculations, that we are now in this zone here. So we are not providing the fit spacing as equal to 90 millimeter from point B to point E, but we are extending that one to the distance D from here. Now that is given in the clause 8.3.2.3. Now if you read it here, I think I showed this one previously as well, that this clause 8.3.2.3 has clearly mentioned distance D from the cross section in the direction of decreasing shear. So that is written here. So we going to do the detailing in the next video, but we stop here. We found S equal to 90 millimeter. Thank you.